Hello. This is kind of how we're going to present information on electric circuits. I'm also going to provide you information with physics classroom readings and videos by professionals or people who do this regularly on YouTube. But I figured I'd do my best at giving you a shot to understand it based on my understanding and how I present things in class. So there's going to be 3 lectures, the first of which is going to be basic requirements for complete electric circuit. So I'm going to leave this up here. I put lines on these sides of the board to let me know where I can write. So hopefully you can hear things, and then if you have questions about the lectures, you can come to office hours and ask those. So basically what we need in order for electricity to flow in a circuit, we need a complete path. So if I have something like this, where I've got a battery, and oftentimes we think of a battery like this, like a 6-volt battery. This would be a D cell, which is a 1.5 volt battery, something like that. You've got batteries in your phones, you've got batteries in your watches, and things like that as well. But normally what we would think of is we think of a source of energy. We think of one side of the battery as being positive, one side being negative, and that's going to be way too small for you to see. So let me try that again. Something like that, I guess. At any rate, what's going to happen is that would not allow electricity to flow because these aren't connected. And I'm not going to get into the chemical nature of the battery about how one side has more potential energy than another, but we tend to think of conventionally as current flowing from positive to negative. We think of positives as flowing as conventional current. In reality, we know it's electrons that are flowing. I won't get into the details of why people think of positives as flowing. It deals with history and a mistake before people knew whether the charges that moved in wires were positive or negative. However, this isn't all we need. We don't just need a positive and a negative terminal. What we need is we need a conducting path. So we need a way to go from, say, here to here, like a wire. Now, if all I had was a wire between the positive and negative terminals, what would end up happening right now is that would be a short circuit. So this wire we would think under ideal conditions is having 0 resistance. Well, if you have a difference in potential energy from here to here, and you end up having no resistance, that means you're going to have a heck of a lot of current. Technically, it'd be an infinite amount of current. But in reality, most wires have a little bit of resistance, and again, we're going to ignore that for the most part. So normally, what you need for a circuit to function, you need a difference in potential energy, which we call voltage. Voltage is energy per charge, and we need a conducting path. So oftentimes we would show something like this. It doesn't matter how you show it. We could show a light bulb here. Something like that. And once it's connected, lo and behold, the light bulbs would light up. Okay. Now we're going to use circuit elements that are a little more simple than this. Because as you can tell, I can't draw very well. You know that from all year. And so drawing a battery like this every time, and light bulbs and things, is going to be a little bit complicated. There is one thing about light bulbs I'm going to draw in detail a little bit later, though. But I'm going to erase this right now. I'm going to show you the diagrams for how we're going to use things in class. Again, these are going to be on the physics classroom as well. Normally what we'll end up doing is showing a power source with a potential difference, which we measure in volts. It's something like this, either a short line and a long line. Sometimes you'll see multiple short lines and multiple long lines for a battery as opposed to just a power source. The short line is the negative side, and the long line is the positive side. So if I drew just one of those, it'd be something like that. A wire is simply a line. Now normally, if you have a resistor, a lot of times it's a light bulb, but it can be other things as well. So for example, the wire in your toaster that get really, really hot when you want to make toast, those are resistors. And they're resistors because they're made of different material and they're skinnier than most normal wires. So we tend to draw resistors as a squiggly line. something like that. So this particular circuit would have three resistors. And we might label this in terms of the voltage. So let's say this is a 6-volt power source. I would label that as 6 volts. These resistors have resistance in ways that are called, resistance is measured in ohms. So let's say this resistance is 3 ohms. Ugh. The symbol for ohm is the Greek letter omega. Looks kind of like a weird upside down horseshoe. Symbol for volts is V. Well, let's say this resistor might have a 6 ohm resistance, and this one might have, say, I don't know, a 9 ohm resistance. And we'll talk about series circuits later. This is an example of a series circuit. If you want to determine the current in the circuit, you need to understand the voltage and the resistance. So we're going to get into the calculations in just a little bit. Current is the rate at which electricity flows. So it's measured in amperes. Or amps. 1 amp is equal to 1 coulomb, which I think we discussed right before we left, is a giant amount of charge. And that's 1 coulomb traveling through something for every 1 second. So if you had 2 coulombs per second, that's 2 amps, 5 coulombs per second, 5 amps, 0.35 coulombs per second, 0.35 amps. So something like that. Now, so current is measured in amps, but the symbol for current, which is a little bit odd, is I. That's the symbol. You could ask me why that is, and I could BS my way into thinking that I remember that. I don't. I do know that since C is the symbol for coulomb, you wouldn't want current and coulomb to be confused. So that's the symbol for current. V, symbol for voltage. R is the symbol for resistance. Now the units are a little bit different. So the units, if you remember, for current are amps. The units for voltage are the easiest one, volts. The units for resistance are ohms. And the symbol, again, is that weird symbol here. So those are the primary things that we're going to be thinking about. We'll also talk about power a little bit, which is the rate at which energy flows. So come back in just a couple minutes about that. So now I'm going to get into the equations. Ohm's law is the primary equation we're going to use for solving things in circuits. So Ohm's law is a ratio with current. It's a ratio of voltage over resistance. So I is equal to V. Really, it's a potential difference. It's a difference in voltage. So I'll say delta V over R. That's one to remember. Write down if you took your formula sheets out and things like that. So I've seen it also written as V equals I times R. And I prefer this way to think about it because this explains to me that this voltage, which is a difference in energy per charge, or difference in potential energy, is the push that causes current to go. And this resistance is in the denominator, and the more resistance you have, the less current you would have. It opposes a flow of electricity. So that's Ohm's law. The power formula, we determine with power is equal to voltage times current. So if a volt is a unit of energy per charge, that's a joule per coulomb. Current is a rate of flow, a coulomb per second. So if we multiply those together, we get joules per coulomb times coulombs per second. That's joules per second. Well, the units for that are something we've heard of before. 1 joule per second is actually 1 watt. So this is probably familiar to you in terms of electricity, because 1 watt is equal to a unit that a lot of times you'd see on a light bulb. So a lot of times you might see a 60 watt equivalent light bulb, a 100 watt equivalent light bulb, something like that. So that's the big idea. Again, additional resources are in the physics classroom, electric circuits. There's parts of lessons 2, lessons 3, and lessons 4 I think are going to be important, and I'll get that out in the syllabus. Thanks.